All right, let's get started. Okay, so starting today, we are back to our homework schedule. Homework 6 was handed out earlier today. As usual, it's due in a week at 11. And we'll basically have homeworks weekly out except the Thanksgiving week. So the last homework will be due on the last day of class. Any questions on homeworks or logistics? I also expect the second midterm to be handed out by tonight, so that should be done soon too. All right, so as we went over the runtime analysis of Dijkstra's algorithm a bit quickly last time, so I'm not going to go over it again, but just kind of situate where we are so we can again read up in the book. Basically what the algorithm does is maintains a set R of vertices that it has computed the shortest distance from the original start vertex S to. And at any point of time it looks for so if this is my set R, it's looking for something that's outside and it's connected by an edge that's inside. And then at any point of time you keep track of this upper bound d prime w on the distance from S to W. And in this loop you pick one that minimizes its value, you add that, this should be an R, and then you fix the, once you add a vertex W to the set R, at that point you set its distance to be this d prime value. So thing to notice, since in every iteration you're going to add one new vertex and there are at most n vertices, you're never going to run more than n iterations of this loop. And if you were to do things a bit naively, assuming the graph is connected, that is m is at least n or n minus 1, then you can compute the minimum value also in order m time. You just kind of, basically just use this formula literally and just compute it from scratch. And so you can get order mn, and again this is assuming the graph is connected. It's fairly simple. There's actually an m log n time implementation that we quickly went over last time, and I won't go in any detail today, but it's there in the book. But it uses the priority queue data structure, which in turn is based on the heap data structure. And so there's a bunch of stuff that I didn't quite cover in particular related to this runtime analysis. So whatever remains of section 4.4 is a reading assignment. Any questions on the shortest path problem or Dijkstra's algorithm before we move on? Amel.
So for Dijkstra, if you wanted to find the shortest path between two nodes, is it correct to assume that you have to build a whole Dijkstra tree to determine that, or can you just because if you were to just try to determine between two specific nodes, you were to sort of eliminate, you might miss another path that's shorter. So you get to build a whole Dijkstra.
So Amel's question is, do you have to build the whole Dijkstra tree to figure out the shortest path between S and T? I'm not 100% sure. Obviously building the Dijkstra tree is enough, but if you just want the shortest path between a given S and a given T, you might be able to do something better. But I'm not sure.
But in terms of Dijkstra's algorithm, would that be the
In terms of Dijkstra's algorithm, you have to build the entire tree. There's no way. Because in the worst case, the T that you're after might be the last vertex that you add to the Dijkstra tree, right? So you have to explore everything. Any other questions? One thing I forgot to mention, that the proof of correctness that we did for this algorithm followed essentially the greedy stays ahead strategy. Because the way we argued is, if Dijkstra's algorithm at end of any iteration has this set of vertices in S that it has handled, we argued that all of the shortest paths computed are correct, right? So it's not worse than optimal on those set of vertices. So now we're going to look at another problem based on graphs, where we'll actually use the exchange argument to prove correctness. So here's one application of this more general problem. Let's say you're trying to build a fiber network. So this, when I say build, I mean literally build in practice, like dig up stuff and build things. So let's say you're a company that you want to lay fibers and you want to connect n locations, right? So you know where these locations are. And you know, and of course laying down fiber costs money, so what you do know is if you were to put a fiber from location 1 to location 2, how much is it going to cost you? Okay. So given all this information, given given these locations and this cost to connect any 2 of these locations with fiber, what is the cheapest way to lay down the fiber so to connect everything? Okay. Now, the simplest way to represent this as a graph is each of these locations is a node, and if you can lay down a fiber between 2 points, then you have an edge, and the cost will be given as a cost value. Okay. Now, note there could be situations where you cannot directly connect 2 locations, right? For example, they are on different side of a river or something. Right? So it is possible that not all edges are present. All right, so what we are going to do today is define the minimum spanning tree problem, which captures this problem earlier. You might be a bit mystified where tree comes in, because the way I've stated the problem, there is no notion of a tree. The only thing we're asking for is connection. So we're going to show first that under some very mild assumption, in particular if you assume that you cannot lay down a fiber for free. So if the cost is strictly positive, which is a very reasonable assumption, then the best way to connect all of these end locations is via a tree. Okay, so that's what we're going to argue. And so that will formally justify why we call this problem the minimum spanning tree problem. And then we're going to look at greedy algorithms, and in particular algorithms to compute the minimum spanning tree. And unlike, say, the scheduling problems where there were many natural algorithms to come up with a greedy schedule, but only one worked, here, like in the previous case, there are lots of natural algorithms that you would think would work, and in this case you will be right in pretty much all of those situations. Right? So we're actually going to look at 3 algorithms that all work, and I think ultimately we're going to end up proving that 2 of them work correctly. Okay. All right, any questions while I move on? All right, so as I said, this is called the minimum spanning tree, and it's almost invariably abbreviated as MST problem. And so as I mentioned, the way you formalize this is the set of locations and the cost of connections, or which pairs can be connected or cannot be connected, is represented formally by a graph. So you have a graph GVE. We will assume that G is connected. So for example, if in your original set of all possible connections, there is no way to connect point A to point B, just laying down few of those fibers is not magically going to connect it. Right? So we're going to assume that the graph G is indeed connected. We also, just as a reminder, by default all graphs are undirected, so in this case G is also undirected. And you're given cos CE for all edges in E. Okay. Now it turns out that many of the algorithms that we're going to present don't necessarily actually even need this positive cost assumption, but kind of, at least in the fiber example, it makes sense. But I'll just make a note that this is for convenience. In particular, all of the algorithms that we consider can be modified to work even if the edge costs are negative. All right, so what do you want to output? So again, the vertices in V are the location that needs to be connected. The edges in E are the pairs that can be connected, right, due to some physical reason. And what you want to do is just pick the smallest subset of edges that keeps everything connected. So you want to output a subset of edges E prime such that if you look at the graph where the set of vertices is still V, but now you're only using the edges in E prime. Or another way to think of this is you start off with your original graph and throw away edges that are not in E prime. Right? Then the remaining graph that you get is connected. In literature, this smaller graph T is called a subgraph for obvious reasons. Right? You're just picking some of the edges from the original graph. And what you want to do is minimize the total cost. The total cost of this subgraph T is something very obvious, which you look at cost of every edge in the subgraph and add it. Like in the case of shortest path, the length of a path was just sum of the lengths of the path. Okay. So is the problem clear? Are there any questions? I still have to justify to you why this is called the MST problem. Where does the tree come from? But we'll get to that shortly. But any questions on this general problem statement? Okay, so let's maybe do a simple example. If my original graph was this triangle graph where the edges are of weight 1, 2, and 3, what would be a valid? And in case I claim that here there is a unique solution that minimizes the total cost, so what should T be in this case? What edges would you pick? Matt? You pick the one edge and the two edge, right? So the first thing to note is you have to pick at least two edges, right? Because if you don't, then your graph is not going to be connected, right? So if you picked only one edge, you won't be able to connect. Make sure that all the three vertices are connected. And in this case, it turns out one of the simple strategies I can do, which in fact you can convert into an algorithm that always works, is to kind of go through the edges in decreasing order. So try to throw away the edge weight which is maximum. So in this case, you throw the edge with cost 3, and then you're left with a tree that connects everything. You cannot throw anything more because then you'll be down to one edge. And this is the best that you can do. Okay. Any questions so far? Okay, so let's kind of prove a small proposition that will justify using the phrase tree. And so we're going to look at the case where the edge costs are strictly positive, and again in the fiber example this is perfectly valid. Putting down anything will cost you at least non-zero amounts of dollars. Then the optimal solution T is a tree. Okay, and so the reason this is called minimum spanning tree is because essentially if you assume all the edge costs are strictly positive, then the optimal solution is a tree. It's spanning because you're connecting all the vertices, the original set of vertices in your graph, and it's minimum because you're trying to minimize the total cost. Okay, so we'll argue this. This is fairly simple, and so we'll argue by contradiction. So assume T is not a tree. Now note, by definition T is connected, right? So if a graph is undirected, connected, but it's not a tree, what kind of structure does it need to have? Like a cycle, right? Because a tree is undirected, connected, and has no cycles. So if it already is connected and is undirected and is not a tree, then it means it has to be a cycle. Okay. So this implies as T is connected, T has a cycle. Okay. So let's say I have so let me call this cycle C. And what we're going to do, the rest of the argument is simple. Let's just pick any edge. Okay. So let edge E be in C. So let me call this edge E. And what I'm going to do is I'm going to throw away this edge. Can I get a new structure? And then I'm going to argue two things. This new structure is still connected and has a strictly smaller cost. And that will contradict the assumption, our original assumption that T is not a tree. So what we're going to do is delete E from T. What does this mean to get T prime? What this means is the set of vertices is still the same, but the set of edges has one less edge. In particular, it doesn't have E anymore. Okay. So again, remember this is the set difference. So what this means is I'm throwing away the edge little e from the set of edges E. Oh, sorry. I should have a prime because I think I used E prime over here. Okay. And so the first claim is that T prime is still connected. And we'll see shortly why this is true. And the second claim is the cost of T prime is strictly smaller than cost of T. So let's try to argue. Okay, so let's see why these two is enough. If both of these are true, note that T prime satisfies all the properties that's needed from the output, right? It connects all the vertices, but its cost is strictly smaller than cost of T. And this contradicts the assumption that, or contradicts the fact that T was an optimal solution. Okay, so this contradicts the fact that T is an optimal solution. So now let's quickly go over the arguments for why both of these claims are true. To see why claim 1 is true, now what can go wrong if I throw away a vertex? Right? The only thing that can potentially go wrong is there were two vertices that were connected in T, but now suddenly once I throw away this edge, they are no longer connected. Right? If every vertex still remains connected, then I'm fine. Okay? So let's say you had two vertices X and Y, and in your mind, the way you had rationalized to yourself that these two vertices were connected was because there was a path that included E. Okay? So let's say there was a path from, so the reason you thought X and Y were connected was because you took the path from X to E, took the edge E, and then from E onwards, another path to Y. Right? And so now you're saying I'm throwing away the edge E, but X and Y are still connected because you can kind of take the long path. Right? So instead of taking that short edge, you take the rest of the cycle, and X and Y still remain connected. Okay? So this essentially argues that any pair of vertices that were originally connected still remain connected, and since our assumption originally was that T is connected, this means that the new T prime is also connected. The argument for this is even simpler. The thing to note is cost of T prime is same as cost of T, except you're throwing one edge away, right? So this is exactly C of T minus cost of E. And here we use the fact that all the edge costs are strictly positive. So you're subtracting a strictly positive quantity away. So this means this is strictly smaller than C of T, as C of E is strictly bigger than 0. Okay. And so that's it. And so we have argued that if all the edge costs are strictly positive, then the optimal solution is always a tree, and this justifies the name of using a minimum spanning tree. Okay. So talk to your friends for half a minute. Let me know if you have any questions. If not, think about ways you can solve this problem. So try to think of algorithms that you can use to solve this problem. right, let's come back. Blake, you had a question?
Yeah, I was wondering how can you find the shortest path where you do have negative points? Like if you get a positive or negative points?
Wait, do you mean shortest path or minimum spanning tree?
Shortest path.
Let's talk about offline because it's minimum spanning tree. Okay. And we will look into it in the last couple of weeks in the course. Any questions on this problem that we are looking at, minimum spanning tree, the argument why the optimal solution is a tree and all the edge costs are strictly positive? Okay, so let's try to think of algorithms and let's try to think of the most simplest one. So what would be a brute force algorithm to solve this problem? Mehmet. You might want to check something more than just a path. Right, so you in general, if you know all the edge costs are strictly positive, you might want to check all possible trees, but then quickly generating all possible trees is kind of a bit annoying. So what you can do is just look at all possible subset of edges, right? Because that's what the solution says, right? So the brute force algorithm is look at all possible subsets of edges E prime and check whether those subset of edges connect all vertices V. If so, keep track of its total cost and then just go through all of them and output the one that is minimum cost. So the brute force algorithm is go over all possibilities of subsets E prime of E and check if the set of edges E prime connects all the sets of vertices. If so, compute its cost and keep track of minimum cost. So this obviously will work. Yes, as a quick question to see how much you guys remember about subsets and stuff. How many such subsets E prime can you have? Mehmet? 2 to the m. The original set size is of size m. There are m edges, so you're looking essentially at the power set of a set of size 2 to the m. Right? So there are 2 to the m subsets, which clearly is not nice, right? So we want something that's polynomial in m and n. So talk to your friends for a minute. Try to think of some greedy algorithms that you can use to solve this problem. And for simplicity, you can assume all the edge costs are strictly positive. So what that means is you know that you're looking for a spanning tree. All right, any questions? Okay, if not, any suggestions for greedy algorithm or algorithms to solve this problem? Jordan. Sorry? Jared, sorry.
Would it be sorted then by the cost of the edges?
Increasing or decreasing?
Increasing.
Okay.
So the cheapest one and remove all the outgoing edges, all the edges connected to the first.
Okay. If you remove, so suggestion is you pick edges in increasing order of cost, pick the cheapest one. You don't want to throw away edges immediately, right? Because if your original thing was a tree and you throw that edge away, you're in trouble. But let's say the idea is you're getting on the right track. You want to, for example, make sure that the cheapest edge is in there, right? And you want to keep on doing this, like go the second cheapest and so forth. When do you think you should not add an edge? Right, so or put another way, you're trying to add an edge. If these are already connected, you're introducing a cycle and you don't want to do that, right? Because we just saw you throwing away an edge from cycle. So great. In like 2 or 3 minutes, we came up with this algorithm which is correct, and this shows the value of being born early enough. So this algorithm has a name because the dude who invented it started working on this problem before anyone did, right? So, all right, there are at least two other possible algorithms here. Mehmet.
Start out with the full graph. Start moving the largest edges with that.
Sorry, saying so start out from the edges from largest to smallest and try to throw them away unless it gets disconnected. Yeah, so this one is not named after someone, but it's called the reverse delete algorithm, and it also works. Any other suggestions? So it turns out there's another algorithm that will look very similar to something that we have seen. So I'll come to it when we get there. So this is the algorithm that Jared came up with. It's called Kruskal's algorithm. This was invented by Joseph Kruskal, I think sometimes in the 50s or so. At that point, he was working for AT&T, which I don't know how much if you guys know history. At that point of time was the monolith. So they were the only ones who had phone companies, and they had lots of interest in laying down cables and things like that. And so this kind of problem that was interesting to the company. And so here's the algorithm. So again, remember the input is a graph with set of vertices V and sets of edges E. And let's assume for now that all the edge costs are strictly positive. So this, I'm overloading notation a bit. I'm denoting T to be the set of edges instead of the whole subgraph. So you sort the edges in increasing order. You consider the edges in that increasing order one by one. And if that edge can be added to whatever you already have in this set T, and that does not introduce a cycle, you're done. You just put it in. And you just keep on doing this, right? So basically what you have to do is you just go through the edges in increasing order of cost. If you can add it, i.e. adding it does not add a cycle, you add it in, otherwise you throw it away. Otherwise you don't add it. Okay, and this is the algorithm. Now note that this is a polynomial time algorithm because you can sort in polynomial time. You're looking at m edges in order, and you guys have already seen in one of the homeworks how to, at least in polynomial time, check whether a graph has a cycle or not. So you can definitely solve this problem in polynomial time. It turns out you can do better than what I said, but at the very least, this is definitely a polynomial time algorithm, much better than the exponential time brute force algorithm we just talked about. And intuitively, it seems to make sense, and so we're going to argue formally that that indeed is the case. Okay. So the other algorithm which no one proposed is somewhat similar to Dijkstra's algorithm, and in some sense is actually simpler. So I'm changing what was R to S, and I have a good reason. I'll come to a notation later on where S makes a bit more sense. And you pick any arbitrary vertex to be called the start vertex, and you build this set of vertices S that you have taken care of. Right? And again, you have this set of edges T. And you repeat the algorithm till you have not taken care of everything. Right? So till S is not same as V, you look at all the edges that I would call a crossing edges. So one endpoint is in S, the other endpoint is outside of S. And among all such crossing edges, pick the one with the minimum cost. Okay? So if this edge E was the minimum edge cost, minimum cost edge, then you add E to this set of edges that you're building, and you also add W. So the idea is, like in Dijkstra, when you figured out, the next guy W, you add it into your set. Okay, so you had the set S, you pick the edge with the minimum crossing, minimum cost crossing edge, and you put the other endpoint inside of this. Okay, and you keep on doing this. So let's run through an example of this algorithm. So here's a example graph that I made up. So, and let's say I start off with this right bottom vertex as my start vertex. It really doesn't matter for the algorithm in the proof or runtime analysis which one you pick. I just happen to pick that one. Okay. So in this case, the two crossing edges are one of course 50 and 51. So the algorithm says pick the one with 50. Right? So I pick 50. And so now I have these two vertices that are taken care of. Which one should the algorithm pick next? .5, right? So the crossing edges are, of course, 0.5, 2, 3, and 51. So 0.5 is the smallest, so that's the one you pick next. Right? What's the next edge to be picked? 2, right? So the crossing edges now are 2, 3, and 51. So you pick 2. Which one goes next? 1. So the crossing edges are now 1, 3, and 51. And note that we are done now because we have put all the vertices in my set S, and that's my terminating condition. Okay. It's not too hard to convince yourself that this is actually the MST for this problem. If you're not, we will argue that this algorithm is correct. So at some point, we would have argued that this is indeed the MST. But you can think about it for a bit and convince yourself that this is true. Okay. So the other one is Mehmet's algorithm, and so this is what's known as reverse delete. So here, the set of edges that we start off with is everything, and now we sort the edges in decreasing order of their cost. So instead of going from smallest to largest, we go down from largest to smallest. And when we are considering edges in this decreasing order, of course, if we can remove that edge without disconnecting what remains, you go ahead and remove it. Okay. So let's run the algorithm on this graph that we just saw. So in this case, what should be the first thing we should try to remove? Which edge? Mehmet? 51, that's the largest, right? You should always try to remove 51, right? So we try to remove 51, we remove it, the graph is still connected, so we are fine, we move on. Okay. The next one we do is 50. If we remove 50, then the graph becomes disconnected, so we cannot throw this away, so we put it back. The next is 3, we remove it, the graph still remains connected, so we move on. We do 2, but removing 2 disconnects it, so we put it back. We try 1, we remove it, the graph becomes disconnected, so we add it back. We try 0.5, we remove it, the graph becomes disconnected, and so we come back. And that's it. So if you might have noticed that the MST that we produced this time is exactly the same as the previous time. And that's because for this graph that we started off with, this is the unique MST for this graph. So all the algorithms should output this graph. Any questions? Marcus.
Will the smallest edge always be in the result?
Mark's question is the smallest edge always going to be in the result? Great question, think about it. I would say whatever you're thinking is probably the right thing, you just have to argue to yourself that it's true.
Okay, so I'll save this for later.
I can ask another question that we can also talk. So the converse of this question is, can we always drop the max cost edge? Alex, why not?
What if the largest edge was that outlier?
Right, so it is possible that your largest edge, for example, was this 0.5 guy, then if you dropped it, then you couldn't do it, right? Or even a simpler example is if your original graph is a tree, then you cannot drop any edges, right? So there exists graphs where, for example, you cannot drop any edges just because your thing to begin with is a tree, right? So it is false to say that it is guaranteed that the max cost edge is never going to be in the MST. It can be, okay? But in the reverse delete algorithm, that's always the first on the chopping block. Okay. Any other question? Amel.
The step of determining if, when you remove an edge, if the graph is still connected, would that be like n plus n every time?
Right, so Amel's question is a good question. So let's kind of quickly go over the runtime analysis and I'll come and answer your question. So again, we have a loop that runs for m times, and every time you have to check whether the graph is disconnected or not. You can definitely do each single check in O of m plus n time by using BFS, DFS, Explore, whatever one of the, however many algorithms there are there, right? So that seems to suggest you need something like m squared or m times m plus n. But it turns out that's not the best you can do. So you can have a much nicer data structure that allows you to, I think, on average, do this in log n time. So you can do much better than that. Any other questions? All right, so it turns out that MST and algorithms for MST have an old history, and in particular, the very first, okay, let me see how much information. The very first algorithm for computing the MST predates even Turing, who was considered to be like, that's generally considered to be the starting point of computer science, which is like 30s, right? So this even predates Turing. So there's a very nice algorithm due to Borowka, and I think if we have time during one of the recitations, the TAs will go through this algorithm. It is not like any of the three algorithms that we've seen. So I know of at least 4, the 3 that we have considered, and Borowka's algorithm that solves the MST problem. There is algorithm due to Yarnik from the 30s. I forget which one this maps to, but it does map to one of the 3 that we have considered. Kruskal was from 1956. Prim's algorithm is from 57. Do any of you guess who this guy is? I have to ask your name, I forgot. Kyle.
It's Dijkstra.
It's Dijkstra. Much younger. So it turns out in 1959, Dijkstra proposed an algorithm to solve the MST problem, which is actually exactly the same as Prim's. And what makes it even more remarkable that they actually worked in the same company. So I don't know what's happening, but it's a fairly natural thing to think of. Okay, so what I'm going to do is so what we have seen are 3 algorithms. Actually, we will not formally prove the correctness of reverse delete algorithm, not because it's not interesting, just because I think you guys will get fatigue of proving correctness of MST algorithms over and over again. We are going to prove the correctness of Prim's and Kruskal's, and one of the reasons to do that is there is a core lemma that you use to prove both together. Okay, so we're going to prove that core lemma first and use that to prove correctness for both Kruskal's and Prim's. Okay. And the runtime is something that we'll ignore, and again, not because it's not interesting, but there are lots of interesting data structures that are going on. I'm just going to assign them as reading for you guys. All right, so we're going to prove something called the cut property lemma. This I don't think is a formal name. I don't think the book uses it. I think I just made it up at some point. But there is an assumption in the cut property lemma, which is we assume all CEs are distinct. Okay? So note that this is in some sense stronger than assuming that they are all strictly positive. I'm saying they are all different values. Okay, so all the M edge costs are different numbers. Excuse me. Under this assumption, we can prove the following. Consider any subset S of vertices which is not empty, so that whatever remains is also not empty. So what I'm saying is S is not empty and S is not everything. So you're kind of dividing the set of vertices into two non-empty parts. And this in literature is called a cut. So another way to think about it is you take a graph and literally just cut everything into two parts. So we call S and V minus S to be a cut. And what the cut property lemma says is for all cuts S and V minus S, look at all crossing edges. By that I mean one endpoint is in S, the other endpoint is outside of S. And so literally, if you were to stretch your graph and put a knife through it, these are the edges that are going to be broken into two, which you can't see. And so what the cut property lemma says is the following. Again, assume all the edge costs are distinct. Then for every possible cut, look at all the crossing edges. Pick the one which is the minimum cost. Now by the assumption that all edge costs are distinct, there is a unique such edge E that crosses this cut. And what the cut property lemma states is this special edge with the minimum cost is going to be present in all possible minimum spanning trees of this graph G. Let E be the cheapest crossing edge. That implies E is in all MSTs of G. Now the reason why this is the way we're going to use it and why this is useful in proving correctness of the MST algorithms is what we're going to argue is for prims and Kruskals, every edge that's added by the algorithm satisfies this property. So in other words, what this is giving you is a notion of a safe in any algorithm. So what this means is if you can show that every edge that an algorithm adds to its final output is a cheapest crossing edge in some cut, then the algorithm cannot go wrong, right? Because it's guaranteed to be in all MSTs. So in particular, that choice is fine. Okay. So the high-level idea going forward is we're going to argue for every edge that's added by prims and Kruskals, there is always a cut, and that edge is guaranteed to be the minimum cost edge in that cut. And so in that sense, every edge that's added by prims and Kruskals is fine. And so that's at a high level the proof going forward. Are there any questions on the statement? Alex.
Couldn't I make a cut so that E is the largest edge in the entire set E?
So you're saying, could there be cut where the edge E is the only crossing edge? Yes. And in that case, you have to put it in. Because if there is only one edge that's connecting two parts and you remove it, then you have two disjoint guys. There's no way you will be able to connect them together. So yeah, so if an edge has just one crossing edge, That by definition has to be there in all instances. Any other questions? Okay, I have 4 minutes. What I'm going to do is open the floor for questions. You can ask 331 related questions that I'll start off with. If not, and please don't leave till the time's done. And if not, you can ask me any questions that you want. If the question gets to be something that I don't want to be on record on, I'll ask Anand to turn the camera off. Blake.
What was the minimum grade of the midterm?
What was the minimum turn to get? I don't remember. We have not calculated it yet. It's not nice, unfortunately. Anand, actually, can you just turn it off? Yeah?